Section 16 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy. Chapter 12, Part 1. For all time Venus has been known as evening and morning star. By the ancients it was supposed to be two separate bodies which were named Phosphorus (Lucifer) or morning star, and Hesperus (Vesper) or evening star. For Pythagoras in the 6th century B.C. has claimed the honor of discovering the identity of the two stars, but it was probable that he restated the views of Eastern astronomers. As the most brilliant star in the heavens, Venus is certainly the one that has always been most observed. Glittering in the sky like a clear diamond, its pure white light, which on a night where there is no moon is strong enough to cast a shadow, naturally would impress all whose lives are spent out of doors. Hence Venus has always figured in literature as the shepherd's star. Homer speaks of the planet as Callistus, the beautiful, and as a type of beauty, its worship figures in all mythologies. At a time when the planets were personified as gods and goddesses, it is easy to understand why this star was selected to typify love. Not only on account of its splendor in the evening sky, but for other phenomena, Venus is familiar in history and literature. The historian Varro (116 28 B.C.) states that Aeneas, on his voyage from Troy to Italy, saw this planet constantly above the horizon, and the same historian is quoted by St. Augustine as speaking of a change in the color and brilliancy of Venus. In 1716, the visibility of Venus in full daylight was hailed as a marvel by the people of London, and in 1750 its appearance at noon aroused general astonishment in Paris. Again, in 1797, when Napoleon returned to Paris from his conquest of Italy, he found the attention of the populace divided between his reappearance and a similar striking midday phenomenon. In fact, Bonaparte always associated this star with his fortunes, and one evening, while engaged in viewing the starry heavens, pointing to the planet, said to Prince Talleyrand, "Do you see? That is my star. So long as it shines, I will have no doubt of success." In more recent times, many brilliant appearances of the planet have been observed, the interval between periods of greatest visibility amounting to 8 years. At one of these, in April 1905, at Cherbourg, Venus appeared as a bright meteor of appreciable size and full form, an effect which was due partly to the formation of a halo. According to the Ptolemaic theory, Venus was always between the Earth and the supposed orbit of the Sun. Hence it was possible that, at the most, but half of its illuminated surface could be visible to the Earth. When Galileo, with his telescope in 1610, made the striking discovery that Venus appeared in various phases, just as the Moon, exhibiting the gibbous as well as the crescent phase, it was a strong and almost the last argument necessary to establish beyond question the Copernican theory that the planets revolve around the Sun. Were Venus as large as Jupiter, for example, the phases would readily be discerned by the unaided eye. Indeed, Sir Robert Ball has wondered what would have been the effect on the history of astronomy had Venus been of the size of Jupiter, so that its crescent form could have been seen without a telescope. Then the elementary truth would have been apparent, that Venus was a dark body revolving around the Sun. The analogy between it and our Earth would have been at once perceived, and the theory of Copernicus long since might have been established. The mean distance of Venus from the Sun is 67,200,000 miles. With the exception of the Moon and an occasional comet, No other heavenly body comes so near the earth at any time. The orbit is marked by the smallest eccentricity in the planetary system, and is therefore more nearly circular than that of any other planet. The planet's greatest and least distance from the Sun vary from the mean only by about 470,000 miles each way. Venus is the nearest planet to the Earth, as there is only 26 million miles between the orbits of the two at inferior conjunction or their nearest approach. Yet Venus is not as well known as Mars, since when Venus passes nearest the Earth it is then between it and the Sun, so that the hemisphere which is illuminated is not visible to the Earth. The appearance of Venus in the sky as the evening and the morning star was no less impressive to the ancients than the beautiful character of the star itself. It is as familiar now as it was to the shepherds of old that when Venus disengages himself in the evening from the rays of the setting sun, it departs from the Sun a little more every night, increasing its brilliancy until a certain distance in the east is reached, appearing, like the Moon, to travel toward the left of the observer. At the end of a few months it has removed itself from the Sun to an angular distance that may amount to as much as 48, at which time the planet sets more than 3 hours after the Sun. After shining for some months, little by little the planet begins to return toward the Sun, receding more and more from the Earth, then passing behind the central luminary and thus ceasing to be the evening star. After an interval a new star is seen in the early morning, to precede the rising of the Sun, advancing by imperceptible degrees every day, and eclipsing likewise all the bodies of the heavens by its dazzling light. At this time it proceeds toward the west, that is, toward the observer's right hand, and we have now the morning star. After having preceded the rising of the Sun by 3 hours, Venus resumes its course anew toward the Sun and again is lost in the glare of day. It is then passing between the Sun and the Earth, and is at its greatest proximity to the Earth. Sometimes it passes just in front of the Sun, as it did in 1874 and 1882, which phenomenon is known as a transit. As it happens but twice in a century, a transit is an occurrence of considerable importance to astronomers. These transits are valuable for the easy determination of the position of the planet, for the investigation of its atmosphere, and for the determination of the solar parallax by comparing the amount of apparent displacement in the planet's path across the solar disk when the transit is observed at widely separated stations on the Earth's surface. These transits occur in June and December, taking place in cycles whose intervals are 8, 105.5, 8, 121.5 years. They have occurred on the following dates: December 7th, 1631, December 24th, 1639, June 5th, 1761, June 3rd, 1769, December 9th, 1874, December 6th, 1882, and will occur again on June 8th, 2004, and June 6th, 2012. The first observed transit, namely that of 1639, was watched in England by two persons, Jeremiah Horrocks and a friend, William Crabtree, whom Horrocks had forewarned of its occurrence. That the transit was observed at all was due entirely to the remarkable ability of Horrocks. According to the calculations of Kepler, no transit could take place that year, 1639, as the planet would just pass clear of the lower edge of the Sun. Horrocks, however, worked the question out for himself, and came to the conclusion that the planet would actually traverse the lower portion of the Sun's disk. The event proved him to be right. Horrocks, who was said to have been a veritable prodigy of astronomical skill, unfortunately died about 2 years after the celebrated transit, in his 22nd year. The transits of Venus next observed in 1761 and 1769 were taken advantage of by Edmund Halley to suggest a means of ascertaining the distance of the Sun. The idea had originated in rather vague form with Kepler, but was suggested more definitely by James Gregory in 1663. After Halley had observed the transit of Mercury in 1677, he realized the advantages of the method and published several papers urging preparations for observing the transit. He pointed out, says Berry, treating of this point in his Short History of Astronomy, that the desired result could be deduced from a comparison of the durations of the transit of Venus as seen from different stations of the Earth, i.e., of the intervals between the first appearance of Venus on the Sun's disk and the final disappearance as seen at two or more different stations. He estimated, moreover, that this interval of time, which would be several hours in length, could be measured with an error of only about 2 seconds, and that in consequence the method might be relied upon to give the distance of the Sun to about 1/500th part of its true value. As the current estimates of the Sun's distance differed among one another by 20 or 30%, the new method, expounded with Halley's customary lucidity, was an enthusiasm not unnaturally stimulated astronomers to take great trouble to carry out Halley's recommendations. The results, however, were by no means equal to Halley's expectations. Immense trouble was taken by governments, academies, and private persons in arranging for the observation of the transits of 1761 and 1769. For the former, observing parties were sent as far as Tobolsk, St. Helena, the Cape of Good Hope, and India, while observations were also made by astronomers at Greenwich, Paris, Vienna, Upsala, and elsewhere in Europe. The next following transit was observed on an even larger scale, the stations selected ranging from Siberia to California, from the Varanger Fjord to Otaheite, where no less famous a person than Captain Cook was placed, and from Hudson's Bay to Madras. The expeditions organized on this occasion by the American Philosophical Society may be regarded as the first of the contributions made by America to the science which has since owed so much to her, while the Empress Catherine of Russia bore witness to the newly acquired civilization of her country by establishing a number of observing stations on the soil of her empire. A variety of causes prevented the moments of contact between the disks of Venus and the Sun from being observed with the precision that had been hoped. The values of the parallax of the Sun deduced from the earlier of the two transits ranged between 8 minutes and 10 minutes, while those obtained in 1769, though much more consistent, still varied between 8 minutes and 9 minutes, corresponding with a variation of about 10,000,000 miles in the distance of the Sun. The whole set of observations was subsequently very elaborately discussed in 1822 to 1824, and again in 1835 by Johann Franz Encke, who deduced a parallax of 8 minutes 57 seconds, corresponding with a distance of 95,370,000 miles, a number which long remained classical. The uncertainty of the data is shown by the fact that other equally competent astronomers have deduced from the observations of 1769 parallaxes of 8 minutes 0.8 and 8 minutes 0.9. End of section 16.